Welcome back to Honors Calculus. In this video, we're going to be looking at the mean value theorem. The mean value theorem is the last of the three big theorems of calculus. These are the theorems that rely on the completeness axiom. They are crunchy proofs that are going to involve um, some technical detail and probably some annoyance. And they're also noteworthy as being existence proofs that tell us that a thing happens, but don't give us any information on how or when it happens. Even so, they are powerful and they are useful tools in the pursuit of mathematics, so they're things that we really have to make sure that we understand or at least can accept. Just like the other theorems of this sort that we have talked about, to prove the mean value theorem, we have to start with a relatively simpler theorem. In this case, it's going to be Rolle's theorem. So let me get my head out of the way and let's dive in. Rolle's theorem asks us to consider a function which is continuous on a closed interval from a to b and differentiable on an open interval from a to b. And even more conditions, such that f of a is equal to f of b. That is an incredibly specific starting point. We need a function which is of equal value at two endpoints of an interval and is continuous and differentiable everywhere on that interval. Right? Differentiable on the endpoints of an interval is not something we've defined, so that's why we have to have differentiable on the open interval. Continuous on a closed interval we have defined, so that is something we need, and it is something that will make a difference. We need to make sure we have it. And the claim here of Rolle's theorem is that there must exist a point somewhere in the middle such that f prime at that point is equal to 0. And the proof here in the first case, the one easiest way to get f of a equal to f of b is that f of x is equal to, not necessarily 0, I'm getting ahead of myself, f of x is equal to some value, let's call it k, for every value of x in the interval. Well, the derivative of a constant is 0. So that's easy enough. Then we get to the natural case, which says that f of x has to vary. And if you think about this picture, something has to happen. At some point, this curve has to either go upward, which means that it also has to turn around and come back downward. Or this curve has to go downward, and then turn around and come back upward. If it goes upward first, then there has to be a maximum. If it goes downward first, then there has to be a minimum. More probably, it's going to do all sorts of stuff. It's going to have several maximums and several minimums. Entirely possible that it has a ton of them, but it has to have at least one. So if the function varies at all, the only way to start somewhere and get back to where it started is to have an extreme value appear somewhere in that list. And extreme values must occur at critical points. Which means that f prime of c equals 0 or f prime of c is undefined. But we said in our assumptions that f was differentiable. And because it is differentiable, that means that it's never undefined. It must be the case that the derivative is equal to 0 at that point. There's our theorem. From here, we'll go onward. That's actually all we need in order to prove the mean value theorem itself. The mean value theorem has basically the same setup. Let's let f be continuous on the closed interval from a to b and differentiable on the open interval from a to b. And I claim here that there exists a c in the interval from a to b such that f prime of c is equal to f of b minus f of a all over b minus a. I think this takes more understanding what I'm claiming than actually proving. So let's start there. Let's draw a quick graph of a function. Let's have a down here. Let's have b up here. Let's try drawing that as a straight line. I'm going to draw a straight line through those two endpoints, or as close as I can through those endpoints. The slope of the line is the change in y over change in x. And the claim here is that there is some point C so that the tangent line at that point is parallel to the line in blue, which is called a secant line. It could be that that happens in more than one place. And in this particular curve, it does in fact happen at more than one place. It happens right there as well. Again, the mean value theorem is an existence theorem. It says that the thing happens. It doesn't say that it happens exactly once. It doesn't say where it happens. It just says that it will happen. All right. The proof of this theorem is visually very simple, but mechanically very messy, as is the case in all of the major theorems that we've talked about in calculus. What I want you to imagine is taking this curve, grabbing those two endpoints, grabbing the blue secant line, and wrenching it so that that blue secant line goes perfectly horizontal. We're going to perform a transformation. We're going to create a new function by taking the curve, f of x in yellow, and subtracting from it the blue secant line. And what we'll do by doing that is translate this graph so that it collapses down and falls along the x-axis. The blue secant line will go along the x-axis, and if you tilt your head, you'll see where the rest of this graph goes. All right, doing that is not easy, but seeing it is quite a bit easier. Let me get my head out of the way and let's actually do this proof. All right, so we're going to make a function g of x, which is f of x minus the equation of that line, which is going to be f of b minus f of a all over b minus a times x minus, we can choose either a or b. I'm going to choose a plus the y value, which is f of a. I claim that g of a is equal to 0 and g of b is equal to 0. I'm not going to take the time to go through that algebra. I would like you to do that on your own. I would like you to evaluate g of a and g of b and verify that you get 0 in both cases. Once we have that, the rest of this is fairly straightforward. There must be a function, or must be a point C somewhere in A of B, so that g prime of C is equal to 0. Right? Now, if I differentiate this horrible, nasty mess, I get a horrible, nasty mess, but a little bit less of one. All right, so g prime of x is going to be equal to f prime of x minus the derivative of all of this. What I want you to see is that all of this is a constant multiplied by this function, and the derivative of this function is 1. So constant times function whose derivative is 1 gives us constant, and then this is a constant by itself. Derivative of constant is 0. So I get that g prime of x is equal to f prime of x minus f of b minus f of a all over b minus a. And g prime of c then is f prime of c minus f of b minus f of a all over b minus a. But g prime of c is 0, so I get that this is equal to 0, which means that f prime of c is in fact equal to f of b minus f of a all over b minus a, which is what the theorem said we were going to get. All right. All that leaves is that little bit of algebra that I asked you to try to verify that this theorem, or that this function that we created, this g of x, actually does satisfy the conditions for Rolle's theorem. So take a few minutes, see what you can do with that one, and I'll see you in the next video.